All right, I had so many mistakes in that last one. I had to start over. Oh, the joy of editing. It's Wednesday, St. Patrick's Day, March 17th. And we did number 29. It looks a little different in the notes because I went in and cleaned that up here, a little less messy. One thing I didn't put in here was on 29. These guys cancel. So basically 29 was showing that as Galileo discovered all things fall at the same rate in a vacuum, he figured that out by rolling things down the ramp. And this question is showing that, hey, you roll things down the ramp, as long as it's the same shape, same distribution of mass, same moment of inertia, the one that's twice as massive has twice the weight down the ramp, everything cancels. Okay, the next one was 33, and I cleaned this one up a little bit, reorganized it, made it a little neater. Our initial angular velocity was 0, and you had to find the final angular velocity was pi. And if you're spinning this like a disk, like we did the granite sphere at St. Rita's, except we did that one virtually. So torque is I alpha. Put mr squared over 2 for a disk in for I. Alpha's still there. Force times radius. Force is what we're after. The radius, one of those cancels because you're applying the force at the outside edge of the disk, so the radius is the same thing this time. Just be careful with that. Omega finals is equal to omega initial plus alpha times delta t. If you subtract off the omega initial, divide by time, you got omega final minus omega initial equals t final minus t initial is angular acceleration. That's 0, so I just took it out. And then I substituted this in for alpha. And then you just put the numbers in there and you're good to go. Comes out to 177 newtons. By the time you round it to the 2 significant figures you're supposed to have, you come up with 180. Okay. Here's the one I botched earlier in the video, so I had to. Okay. We didn't do this as a lab, but we could have. We're just not going to go back and do it now. But if I took that big wheel I've got, that measuring wheel that's 5 feet circumference, and I put 2 different masses on them when we let them go, now that wheel is big enough and massive enough and large enough radius that it slows that down. Earlier we did an Atwood's machine lab like that a couple months ago back in the corner, where we had a pulley that was small and didn't have very much friction, wasn't influencing things. But with a bigger mass to turn, then you got to take it into consideration. So we're going to call a 5 kilogram mass a driving mass. And then coming off of that, we're going to have a resistance here. We're going to call everything positive clockwise positive. We're going to call everything counterclockwise negative. So this driving mass has to get this inertia moving, and that takes a force. It has to get this inertia moving, and that takes a force. Okay, so we take our driving mass minus the tension force here in the string, minus the force to turn the wheel, and that gives us a net force of accelerating both of these tied together. Now if that's confusing or you have a question about it, go ahead and ask. So I confused myself there in the last video and had to do it over. Happens once in a while. Okay, so our driving mass is 5 kilograms times 9.81. Don't use negative on a 9.1 because we're changing our frame of reference. We don't need to worry about down being negative, up being positive. Now we're doing clockwise is positive, counterclockwise is negative. So I'm adding a negative here because this part's counterclockwise, this tension here. I'm adding a negative here because the tension, the force it takes to spin this inertia, the inertia is going to feel like it's in a negative direction. And then we have to accelerate both masses with acceleration A. And I think that might be what we're looking for. Okay? So just like before in the other examples we had, you can't forget that this driving force has to then be used to accelerate both of those. Okay, so when you multiply this to get a number, multiply this to get a number, I ran through this rigmarole again where torque is I alpha. We've got to spin this guy. I want this term right here for the wheel. That's what I'm after right now. This and this was easy. I've got numbers, and we'll have some numbers for both of them. Okay, so for the wheel, torque is I alpha, force times radius is I alpha, because torque is force times radius. I need to get rid of that and get an A in there. So A is R alpha, divide the R out, so A over R we're going to put in for alpha. So I didn't do that here, but I did it here. Okay, we've got I for this wheel. It's 5 kilograms times meter squared. We've got an A. I got my R in there squared, 0.5 meters squared. Equals 7 kilograms times A. So we subtract these, go on to the next page. Go ahead and subtract these and get a number. Go ahead and clean this up. 5 divided by 0.5 divided by 0.5 is 20A. Kilogram is the unit. And 7. So add 20 kilogram times A to both sides. I get 29.43 newtons equals 27 kilograms times A. Divide over the 27, I get 1.1 meters per second squared, means how fast the strain and the masses are accelerating. Or the rate at which, I shouldn't say how fast, the rate at which they're accelerating. Now, if you're this mass, and you're sitting there feeling 9.8 meters per second squared, and then this takes off, that tension is going to get greater. And you're going to feel an additional 1.1 meters per second squared, and you're going to feel heavier there. So your acceleration is 10.9 meters per second squared. On the other side, you got gravity acting on this 5 kilograms at 9.8 meters per second squared. But the whole thing's going to start moving, which will decrease the tension in the string slightly. And you're going to fall in the same direction as the 9.8. So you're only going to feel accelerated by 8.7 meters per second squared because you're giving way. Now if we take both of those new accelerations and multiply this one times 2 kilograms, we get a force of almost 22. This one times 5 kilograms, we get a force of almost 44 newtons. That's how that's done. The last problem is actually easier, number 44. You have a woman sitting out at the end of a turntable. It's a disc. I'm not sure it's a disc. I probably need to change that to turntable. They're sitting there. Their angular momentum is 0 before any motion. After she moves, their angular momentum must still be 0. So whatever hers is positive, the turntable must be negative. Okay? So I'm going to set those to equal to each other and their opposite. So I for the turntable is 530 kilograms times meters per meter squared, because we don't know that it's a disc. I got to change that. We are looking for the angular velocity of the turntable. Because she is, we're going to say, a point mass out at the end of the disc, she's going to traverse the shape of a hoop if she stays on the disc or on the turntable. And the moment of inertia for a hoop is mr squared times whatever her angular momentum or angular velocity would be. Well, we don't have her angular velocity. We have her velocity, her translational velocity, v. But we can tie those two together because we have v equals r omega. So we'll solve for that. Omega is v over r, and we'll substitute that in. Now, because she's at the edge of this turntable, these radius are the same. So one of those cancels. Just be careful with that. They don't always cancel, usually they do. Once you got that, you can put her mass in, radius of 2 meters, velocity 1.5 meters per second, solve for angular velocity for the turntable. And it comes out to be 0.37 radians per second. She goes clockwise, the turntable goes counterclockwise. And is there another question with that? There's some sort of 109 joules in there. I don't have that part done, so I guess I get to do that in the fly. Oh, how much work does she do? Yes, I did. I forgot I did it. How much work does she do? Well, I just calculated the mechanical energy and said work did that mechanical energy, but because it was sitting there. So I just calculated 1/2 I omega squared for the turntable, and for her, a translational 1/2 mv squared for translational kinetic energy, and that's all the energy that was input into the system. It's now mechanical energy, it's kinetic energy, but it was done by work, so we can get by with that. Okay, so you take 1/2 530 kilograms times meter squared times 0.37 radians per second squared, plus 1/2 65 kilograms times 1.5 meters per second squared, and it comes out to be 36.3 joules and 73.1 joules, 109 joules. Now when I first looked at these numbers, I noticed that her kinetic energy was greater than the turntable, and for half a second there I thought I was surprised by that until I realized what was going on. So I want to ask you the question, why is her kinetic energy more than the turntable kinetic energy? Let you think about that. See if you can come up with the reason. Okay, test tomorrow. Ask me if you have questions. I think you're going to be in pretty good shape though. Test questions shouldn't be this hard.